Hey, what's going on guys? Tanmay here for Simple Snippets and welcome back to another video tutorial on data structures and algorithms. And let's continue with our graph topic. We've covered quite a lot of details about graph data structure. In case if you're new on this channel or in case if you've missed the previous videos, check out the link in the video description to this entire playlist. Previously we've talked about what is a graph data structure, the theory about graph, how it is different from tree data structure, the different ways in which we can implement the graph data structure, that is the adjacency list and the adjacency matrix. So we've covered quite a lot of things, but one important aspect about graph data structure that is left out was graph traversal. So when I say traversal, it means basically visiting each and every node in the graph. And you might wonder, why do you need that? That is because at a very basic level, why do you store data in a data structure? So that later on you can retrieve that or use that data, or you can make some changes to that particular data, right? And in order to do that, in any data structure, you have to traverse the different nodes or different data elements that are stored in the data structure, right? Makes sense? Very basic. So this is where, just like tree traversal that we've seen in this DSA course, we also have graph traversal. And the very basic definition of graph traversal is the process of visiting, basically checking or updating or adding or making any changes each vertex in a graph. So this is a very basic definition. I've just shown you the definition over here for theory purpose. If you're making notes, you can note this down or take a screenshot. This is very easy to understand, right? So this traversal are classified by the order in which the vertices are visited. So just like in tree data structure, we had depth first search, level order traversal, and the different ways in which each individual node was visited. In graph traversal, we have two basic methodologies in which you traverse a particular graph. And the two different ways are breadth first search and depth first search. So we are going to individually cover both of them in this video. We are going to see the different process of how breadth first search happens and how depth first search happens with proper diagrams. So make sure you watch this video till the end, because that is where you'll see the working also, with the diagram as well as step-by-step process, right? But just quickly talking about the theory, in breadth first search what happens is one node is selected and then all of the adjacent nodes are visited one by one. Now we know in a graph data structure we do not have a permanent root node, right? So unlike tree data structures, we don't have a root node over here. So when you're traversing, you can basically select any one particular node and select it as the temporary root node, and you can call it temporary root node just for traversal purpose. So let's say you're starting from A. So in breadth first, what we're doing is we select a particular node and then basically along with that node we explore all of its neighbors. So immediate neighbors are explored. So this process is called exploration. And once all the neighbors of A are done, then you either go to B or either go to C. That is, you either go to any of the other neighbor. Now let's say you go to B. So when you come to B, now again you will explore all the different neighbors of B. And you can see B have many neighbors, right? B has C, B has E, B has D. So when you reach B, you again explore all the neighbors of B, and once you have visited all the neighbors of B, then you again hop on to the next unvisited neighbor. So this is how breadth first search works, and I know there would be a little bit of confusion because we'll see the step-by-step working in a minute, so don't worry, everything will be very clear. And moving on to the depth first, in this algorithm, we start at a particular vertex. Let's say you again select A as the starting vertex. Then when the adjacent vertex is found, it moves to that adjacent vertex. So over here you don't explore all the neighbors of that particular vertex. What you do is you select a particular vertex, you go and check that if you're searching for A, you find A over here, or you simply move on to either C or either B. So you don't go to both of them. You make a call depending upon your needs or however you want. It can be random. It is not like you have to visit B first or you have to visit C first. If it is a weighted graph and if these edges have weights, then you can decide on the basis of the weight also. But you simply go to the next. Once you visit over here, you make the appropriate checking whether you're looking for that particular node or not, and then you visit the next. So over here, exploring a particular node is not happening. That is, you don't visit all the neighbors first. You simply jump to one single neighbor, then move on to the next, then move on to the next, so on and so forth. Okay, like this. So this is what depth first search is. and this is how it differs from breadth first. Now again, things would be a little unclear because we still have to see the working. This was just the quick theory. So now let's see the quick individual working of breadth first versus depth first so that it gives us a better understanding. So let's start off with breadth first search. Again, this is the definition, but this is where the actual steps are. These are the working steps. You can also call it part pseudocode, part steps, right? So over here, to perform breadth first search on a graph, we use a queue data structure. Now I'm guessing you guys already know what is a queue data structure. That is because we've already covered that in this tutorial course. You can check that out. So step 1 is to define a queue. So this is where we have defined a queue. The next thing is you have to select a start vertex. So let's say our start vertex is A. Okay, let's select A as our start vertex. Let's move on to next step. So next step is we have to add the start vertex to the queue. So let's say this is the rear and this is the front end of the queue. So you'll add the first vertex A from this place and it will go to the start, right? That's how you add or basically enqueue a particular element. So we've added A, right? Let's move on. The next thing is you print the current vertex where we are at this particular value. So you get the output of A. Alright, so first node is basically traversed or basically visited using the breadth first search. Now as we all know, in breadth first search, once we have selected a particular node, we will explore this node, which means that we will visit both of its adjacent nodes or all of its adjacent nodes. In this case, who are the adjacent nodes of A? We have B and C. So step 5 says add all the neighbors which are unvisited, that is basically not in the queue or in the output, of V to the queue, and it can be in any order. So let's add B and C. So I'll add B and C to the queue. So currently we are done with A, right? So let me just do a tick mark over here because you can see in the output we still have A. We've just added B and C. Now in the queue we move forward. So right now you can see the pointer is at A. Now we move one step ahead. So now the pointer will be at B. So step 6 says repeat step 4 till the queue is empty, or basically till you have traversed all the elements in the graph. Now programmatically, if you are wondering how you figure out when we visited all the entire elements in the graph and the size of the queue, all those things will be there when you actually do the programming. Right now we are just seeing the overall process and the working. Okay, so we will talk about that in detail when we actually implement the breadth first search using C++ programming. That is also something that we are going to do in further tutorials. So do make sure you are subscribed, and don't worry, I will be explaining all that also. There will be a lot of conditions, there will be a lot of if and else's when we actually apply this breadth first search and depth first search, but this is a very simple step-by-step process which is in the form of English, right? So we are just trying to understand the process. So don't worry about the details, we will cover that as we move ahead. So right now we are at B. So this is the current vertex now. So we simply have to print B. So I'm going to print B. So step 4 is done, and step 5 again will be add all neighbors of V. So current vertex V is B, right? This is where we are pointing now. So who are all the neighbors of B? So we are over here. The neighbors of B are A, C, E and D. We've already printed A. So this is done. So we are not going to add that to the queue. You can see C is already there in the queue. So do we have to add that again? No. So what is left? We have left with D and E. So let's add D and E, right? So this is how you determine which element to add into the queue and which to exclude, that is already visited or already there in the queue. So once that is done, once you've printed B as the output and added all the neighbors in the queue, then again you move forward. So now the current vertex V is going to be pointing to C. So B is also done. We've traversed B. Now we are at C. Okay. So what do? Print the current vertex. So C is going to be printed. Next thing you do is add all the neighbors of the current vertex V. Current vertex V is C. Who are all the neighbors of C? We have A, we have B, and we have F, right? We have 3 neighbors to C. So we have to add all these 3 to the queue. But B and A have already been printed and they are already there in the queue. So you don't have to add that. Who is left? F is left. So we'll add F. Once that is done, And since C is already printed, we will move forward. So now the current vertex V is going to be pointing to D. So C is also done. We've traversed C and added all its neighbors into the queue. So once we come at D, we are over here. What do? You print the current vertex, we'll print D. Then you will add the immediate neighbors. B and E are the immediate neighbors of D. They are already there in the queue and B is already printed. So you don't have to add anything else. So the work is done. You can proceed forward because D is already printed as the output. Then you come at E. Again the same process. You'll print E and check all the neighbors. The immediate neighbors of E is B, D and F. All of them are there in the queue and some of them are already printed, so you don't have to add anything extra. So this is where the programming comes into place to check whether things are there in the queue and the output, and then you determine which neighbor is supposed to be added in the queue or not. So since this is there and you've printed the output, you move forward and the last one you print it out. And once you reach the end of the queue, or if there is no further element in the queue, you can conclude that all the neighbors have been added in the queue and all of them have visited at least once, and then you can get this final output, right? So this is the breadth first search, where you visit a particular vertex, you access that vertex, you do the necessary checks, or you find what you're looking for at that particular vertex, because ultimately traversal is done for a particular purpose, right? You don't traverse the entire graph for nothing. Let's say you want to particularly find the vertex F, or you want to find a value inside a particular node. Only then you do the traversal. So you come to a particular node, make that check. If it doesn't satisfy, then you explore its immediate neighbors in any order, right? So if you're wondering, is this the only valid output for BFS? Then no, that is not the case. So in case at the start, let's say when you are at A, after printing A, you could have also added C first in the queue, right? So at the place of B, you could have added C, and at the place of C, you could have added B. So even this is valid, right? So the output would have also changed. So output would have been C and B. So even this is valid as long as you are adding the neighbors properly for a particular current vertex in any order, right? So remember, the output may change, and one output is not the only output when it comes to breadth first search. There can be many other valid outputs. So this was breadth first search, where you use a queue data structure to do the searching. Now let's see how depth first search is done, and that is where another data structure is also used. So in breadth first search, we were using a queue data structure, and in DFS, that is depth first search, we are going to use a stack data structure. So again, the theory is over here, we've already talked about that, but in the steps, first thing is we define a stack. The next thing is we set a current vertex. Again, you'll have to start from any vertex. It is not like you have to start from A or B, because we don't have the concept of root in graph data structure. You can select any one as the starting point. So again, let's say the current vertex V is A. So you'll say add the current vertex to the stack. You'll add A to the stack. It will go at the bottom of the stack, because stack works in first in last out manner. I hope you know first in last out and first in first out and all those linear data structure concepts. We've talked about all of these data structures previously in this DSA course. So step 2 is done. Step 3 is to add the current vertex to the stack. Of course, step 3 is also done. We've added it to the stack. Step 4 is print the current vertex, basically print it as the output. So once you're done with this, you print it, or you access the particular value of that node, and if you don't find it, now you have to move to the next one, right? So step 5 is add any one neighbor which is unvisited, that is not there in the stack, basically, which was not there previously in the stack, and that we have to add it to the stack. So we have to add one particular neighbor of the current vertex. The current vertex V is A, and we have to add it to the stack. So you can either add B or C. Again, this means that there can be more than one way you can traverse and more than one valid outputs, right? So let's add B for the sake of this video, right? We'll select B. Okay. Step 6 is if the current vertex, so we are currently at A, has all its neighbors already visited. So in case if we had visited all the neighbors, we would have popped it from the stack. But currently we've not visited any neighbors, right? So that's why we added B to the stack. This step is only when we've visited all the neighbors. So you can do the backtracking and you'll understand that in a minute. Let's just skip step 6. Let's move on. Step 7 says check remaining vertices in the stack for any unvisited vertices. This is when you do the backtracking. So step 6 and step 7 happens only when a vertex has all its neighbors already visited and you've backtracked, and I'll talk about that in a minute. Then you move forward, repeat the process till stack is empty. So we've done with A, we've printed A, we've added B to the stack. So now the next current vertex is gonna be B. Okay? So we will be this, which is the top of the stack, right? Okay. So again we will jump to step number 4. So we have to again print the current vertex. The current vertex now is B. So we'll print B and move to step 5. In step 5 we have to again select one particular neighbor of B. So it can be anything, okay? It can be E, it can be D, and it can be C. B has currently 4 neighbors. 4 neighbors are A, C, E and D. But A is already visited, right? So this is where you have to check. If the current vertex has all its neighbors visited, then you have to backtrack. Right now for B, A is already done. So we can either select C, or we can go to E, or we can go to D. Remember, this is depth first search. So we have to traverse to the next node. So let's select E for this case, okay? So let me write E, and E will be added to the top of the stack. And this will be the current vertex now. And step 6 and step 7 will be skipped because we still have to traverse all the nodes. So step 8 we will again repeat the process, which is print the current vertex. So let's print E. Once E is printed, then we have to again decide where to hop next. So which are the immediate neighbors of E? E has D as its neighbor, E has B as its neighbor, and E has F as its neighbor. Now remember, B is already done, so we can't select B again. Let's select D in this case, right? Because D is not yet visited. So D will be added to the stack and D will be set as the current vertex. Okay. So this was step 5. That is, add any one neighbor for the current vertex. Current vertex was E and we've added D. Now first thing, we'll have to print the vertex. So let's print D, and now we will have to make the checks. So this step 4 is basically coming after 5, okay? When it comes to writing algorithms and actual implementation, the printing will happen later on. So once you print it, now we will have to check if current vertex has all its neighbors already visited. So we are currently at D, right? This is the top of the stack. D has only 2 immediate neighbors, that is B and E. So you can see from the output, B and E have already been printed, which means that we've already visited them. Now this is where, if the current vertex has all its neighbors already visited, you have to pop it from the stack and backtrack. So basically now you will have to pop D from the stack, that is remove D from the stack, and go back to the node from where you came to D. So where did you come from? You came from E, right? Which is the immediate vertex below it in the stack. So basically now you are backtracking from D back to E. Okay? So again the current vertex is going to be E. The next thing you'll do is, again you'll have to add one more neighbor which is unvisited. Now this time for E, you can see that D is visited, B is already visited, but F is remaining. E has only 3 neighbors, right? E has B, D and F. Out of that, B and D have already been printed, have already been visited once. So now from E, because E is the current top of the stack and the current vertex, from E you can only go to F, right? So now we will go to F, and F will be added to the top of the stack. So this is how backtracking works once you reach a particular dead end. Now F will be printed, and now we will search for a neighbor for F. F has 2 neighbors, you can see there are 2 edges. You can either go to E or you can go to C. We've already printed E, which means that we only have C as an option. So now we'll go to C. So C will be added to the top of the stack and it will be set as the current vertex V. Then it will be printed, and again when you are at this vertex, the current vertex is C, again a check will be made that whether you visited all the neighbors of C. So all the neighbors of C are A, F and B. So all of them have been visited first or previously. So now you can't select any node. So again you'll have to backtrack, right? So what you'll do, according to step 6, if current vertex has all its neighbors already visited, you will pop it from the stack and you'll go back to the node where you came from. So where did you come from to C? You came from F. So you'll go back. So you remove this from the stack. Then the current node V is going to be F. For F, all the nodes have been visited. So you'll pop it back again. So F will be popped out. And then the top of the stack is going to be E. For E also, all the nodes have been visited. You can see the output, right? You can check the values in the output and make sure that all the nodes have been visited. And you keep on popping. So E will also be popped out. We came to E from B. You can see this arrow. So this is the top of the stack. B is also going to be popped out because from B we have visited all the nodes previously. So all the values will be ultimately popped out and the stack will be empty. So now we will reach at step number 8. We have to keep on repeating all the steps till the stack is empty, and once the stack is empty you can come to a conclusion that we have basically visited all the nodes in the graph data structure, and this is our necessary output. Now again, this output could have been different because it depends upon what path you take when you are doing the hop from one vertex to other vertex. If you have two options, you can select any one. It is not necessary that you have to select one over the other. Again, if it is a weighted graph or a directed graph, then the algorithm of course changes, and it depends on whether you can traverse in that direction, or it also depends upon the weight of the particular edge. So if there are two edges, if you can go from A to B or A to C, and A to B is 10 and A to C is 20, then you can, according to your algorithm, make a choice whether you want to take the smaller route or the lengthier route, right? So this all depends upon the use case. So this was depth first search. I hope you've understood the overall process. Of course, as I mentioned, when it comes to implementation, the actual algorithm is going to be a little bit more complex because there will be many conditions and use cases and checks to be performed whether a particular node is visited previously or not. This was just a very basic theory and working with the help of diagram to show you how breadth first search is different from depth first search, and how queue is used in a breadth first search and how stack is used in a depth first search. Okay, so hope you've understood the two different traversal techniques. In further videos, as I mentioned, we will get on with the implementation. Since we've covered a lot of theory on graph data structure, we are now prepared to actually start with the implementation. So make sure you subscribed and turn on the notifications so that you get updated whenever I upload those videos. They will be coming right up after this one. So yes, I'm gonna wrap up this video over here for graph traversal. Hope this video was understandable. If you like this video, please give it a thumbs up. Let me know in the comments how this video was. Do share it with your friends, and I'll see you guys in the next one. Peace.